mess up a lot. But I told the joke in my last class. Can I tell it again? It's all joke. You probably heard of it. What do you get if you cross an elephant with a rhino?
Rhino.
Very good. Who said that? Very good, Macklin. Have you heard that before?
Yeah.
Bursted my bubble. It's okay. All right. I'll tell you another one next time. All right. So anyway, that was, we're going to start in with, this is called trigonometry. This is section 4-1. And trigonometry. Anyone know what Greek words that comes from? Three, basically triangles. And metry is what? Right. Measure. Okay, so basically all of trigonometry comes out of, it's based in triangles, and it's all about triangle measurement and different functions we get from that triangle measurement and all that kind of stuff. There are a lot of real life applications of trigonometry. Anyone think of any? Like sine functions, cosine functions, anyone know? Like waves, sine waves, and yeah. So sine waves, but they're, what about a sine? Where do you see sine waves?
Sound waves.
Sound, okay, so sound waves. I'm just kind of listing some things. Anyone else have any ideas? Any kind of orbits of planets? Orbits of planets are based on sine. You can model them with sine and cosine and all kinds of different trig functions. What else? I have some lists here. Guitar players. Anyone play the guitar? A couple people, right? When a string vibrates or any sound, for like Joe and said, right? A string is vibrating. It can be modeled by a trig, sine or cosine function pretty simply. And the faster the frequency of that string is, right? The higher the pitch. Yes, sir.
That's a pilot.
Pilot.
For flying.
Oh yeah, more like right triangle trig and stuff if you're trying to find stuff, but more like cyclical functions, things that repeat over and over time, like the months of the year. If you lived on a coastline, you would know about the tides, you know about the high and low tides and all that kind of stuff. Those follow trig functions as well. So anyway, pendulums swinging back and forth, which we used to do in the past, but I don't know if we're going to do it this year, but we'll have some kind of lab for you. So anyway, they start off in this chapter with an angle, and they define an angle a little bit differently than you've seen it before. So here's an angle. This part of the angle is called the vertex. You know that, right? But different, other than what you learned in geometry, this is called the initial side. And this side over here is called the terminal side. So an initial is where you start, and terminal is where you end, right? So, and the reason they call it that is because when you measure an angle, you measure it as a rotation from the initial side to the terminal side. And if you're going, that's counterclockwise. Counterclockwise. Is positive. Positive angle. And clockwise, which is the way a clock goes, is a negative angle. So if I go this way, it's positive. If I go this way, it's negative. You guys see? Has anyone seen this before, or no? Yeah, just a couple people. Okay. So for our purposes, we put our angles in standard position. Let me do that again. Where we have an X and Y axis. So standard position, the X axis, okay? So, and the Y axis. In standard position, X axis is the initial side. So if I want to draw a, if I want to make an angle going over, whoops, wrong way. If I want to make an angle going out in the second quadrant over here, the way I would get there, one way I could get to this angle is starting at the initial side and going that way. That would be a positive angle. It's a rotation counterclockwise about the origin, but I could also get there by going backwards. Okay, so I could go like that, right? And that would be a negative angle. So the same angle, the same angle can be represented in more than one way. So unlike geometry, where we only define angles as being between 90 degrees and 180 degrees, in trigonometry you could have negative angles that are infinite, that could be go on forever and ever, okay? And you could have positive angles that go on forever and ever, okay? So another way I could get to this angle is I could start here. You always start at the initial side, but I could kind of go around the whole circle and then keep going and end up like that, okay? So angles that have that start and then that have the same, since they all start with the initial side, have the same terminal side. It's easier for me. Terminal side are called coterminal. All right, in different color. Coterminal. Okay, questions about that? And we'll talk about how to find coterminal. Okay, done? Can I move on? Yes, no? Yes.
Yes.
Roland,
What's the application of the infinite angle?
what's the application of it? Well, if you're a professional snowboarder, right, you'd have to jump up and do like a 720, you know?
Right, but that's just a 720, but an actual infinite angle. What's the
An
application of that?
Well, planetary orbits go on forever. So eventually in the next chapter, so we find this sines and cosines and stuff like that of these angles, but those things repeat themselves over time. And then we model sine and cosine and all the different trig functions are based on this, except instead of graphing them in a coordinate plane, we graph them over time. And so you see so that might, the sines and cosines represent heights of that angle over time. Yes, sir?
Yeah, and then it ends up being like the cosine of 120 and the cosine of 480 become the same answer, right?
Yeah, we're gonna get to that, yeah.
Did you say angles that have the same terminal side or coterminal? Is that saying like 180, 90, or?
No, like, we'll get to that, but, so say this is 120 degrees, okay?
Yeah.
Then I could also get there by going around and ending there. So I could also call that 360 plus 120 degrees, which is what Joan just said, right? Which would be 480 degrees. Yeah. So those two, I could also get there by going backwards, negative. How would I get there? If it's 360 minus 120, so that would be negative 240. So all of those things would be coterminal. I was going to give a couple of examples there, but we're not. You get that? Yeah. So you could get there different ways. Okay. In trigonometry, we we measure things in radians a lot of the time. I would say like 2/3 of the time. A radian is defined as, it's just another unit of measure, but it's convenient when you're doing trigonometry, okay? And so maybe I should change to, what's a better color? I could look at my little palette. How about purple? Ooh. Now let's see what that looks like. So a radian is the measure. Ooh, that looks kind of cool. The measure of a central angle, which is the angle that intercepts. I'll tell you what this means in a second. Draw a picture. That intercepts an arc S. Arc S equal Hi, Jason Stock. Okay, yeah. Equal to its radius, okay? So in other words, if I take, watch this is cool, and I take this, I should have had arrows on the end, but that's okay. And I'm gonna make a circle. Where's my circle tool? Where's the one I want? I don't know, I want the one with the middle. So it's gonna work. There's another, oh well, I'll try this. So here's a circle. Ooh, pretty good, huh? All right, so if I were to measure a radian, okay, when this length here, so this is R, this is S. When S, if I measure this and I measure this, and S, when S equals R, okay, this angle here is, that's 1 radian. Okay, you don't usually put units on radians because radians are a ratio rather than a measure. It's a radian. Radian measures actually the ratio of the arc length, which is S, this is the arc length, to the radius. Okay? So there happen to be, let me make sure, so theta is equal, so theta in radians, and now we call angles theta, now, is always equal to S over R. And when S is equal to R, what is theta? If S is equal to R, that would be 1, right? So a measure in radians is the ratio of the arc length to the radius. I mean, this is more like theoretical stuff that's kind of good to understand where it comes from, okay? One revolution, if we remember from your geometry classes, how do I find 1 revolution around a circle? 2 pi r, right? Remember, 1 revolution, the circumference of a circle is 2 pi r? Yes? So if I want to find what the angle is, okay, when if I want to know theta, when I go 1 full time around the circle, S is equal to, so S over R is equal to 2 pi r over r. So what's theta equal to? 2 pi, okay? So in other words, if I go around here, measure around a circle in radians, is 2 pi. In other words, there are 2 pi radians. 2 pi radians is, that's, radians is equal to how many degrees? 360 degrees. So if you want to figure out about how much 1 radian is, it's about 57 point something degrees. So you would just take 360 divided by 2 pi, and you would get the measure of one radian, like that, okay? So, and it just turns out it's a lot easier to use radians when you're talking about trigonometry than it is to talk about degrees. So there's 6.28 of them. So let's see, so if I were to measure in radians, like 57 point something, then maybe 104 point something, then what's 104 point something plus 57? 160 something plus another 57, like 2 something, and then 1, 2, 3, 4, 5, I think is going to fall over here. 6, okay? So each one of these angles would represent a radian. So there are, they're not exactly, but they're about 6.28 radians in a circle in, well, 1 revolution. Okay? Yeah? Okay. So how do you use this? So then this is kind of useful now. Whoops, I don't like that paper. So 2 pi, I would set up a little table. 2 pi, that's 1 revolution. How many degrees is that? 360 degrees. Okay. Half of a revolution, 1/2 rev, would be how many pi's? How many pi's would that be? Half of a revolution. If 2 pi's is, it'd be just pi, right? So how many degrees is that? 180, right? 180 degrees. And then you could kind of do that. Some ones that come up a lot. 1/4 of a revolution. 1/4 of a revolution equals how many radians? Pi over 2 radians. Good. And that's equal to how many degrees? 90 degrees. And then some other ones that you'll see quite a bit. Pi over 3, whoops, that's, how many revolutions would that be? Pi over 3 would be 1/6 of a revolution equals pi over 3, and that's 60 degrees, right? Because if I take 1/3 of 180, I would get 60. And another one that comes up a lot is 1/12 of a revolution would be what? Pi over 6, which is 30 degrees. Okay? Good. And those are some useful things to know. And then when you label your axes in trigonometry, now that you're well versed, you kind of want to start talking in radians rather in degrees, but I'll go back and forth. So this is 0 radians, but also if I go fully around, it's also 2 pi radians. Okay? This is, how many radians here? Pi over 2, right? 90 degrees. If I rotate it through. This is pi, and this would be, excuse me, who remembers from last year? The down here. So this is pi over 2. That's pi. Here's another pi over 2. So 1 pi over 2, 2 pi's over 2. How many pi's over 2 to here? 3 pi over 2. Okay? So if they say find the sine or cosine or find it at 3 pi over 2, then you know they're talking about 270 degrees. Okay? Questions so far? Okay, so now we're kind of talking about coterminal angles. Can I go on? Okay, so find 2 angles one positive, one negative, coterminal to pi over 6. Okay? So, and if it would help you draw a picture. Okay? So, pi over 6, how many degrees is that? We just tried. It's 30 degrees. Okay? So, if I were going to do that, I draw a little picture somewhere over here. Pi over 6. And so I could either get that, but now I want to talk in terms of pi rather than in terms of degrees. Okay, so it's kind of nice to start thinking in pi. It's kind of like when you're taking a foreign language, you want to try to think in French or Spanish or something like that rather than translate and then transmit back. So if this is pi over 6, what's another way that I could get to this angle? I'd go start here, go all the way around. So what would that be? Not 7 pi over 6.
13 pi over 6.
13 pi over 6. So I'd have to go pi over 6 plus 2 pi. All right? And to find a common denominator, 2 pi over 6 is equal to 12 pi's over 6. Right? So pi over 6 plus 12 pi over 6 gives you 13 pi over 6. Okay? Yeah? How about negative? How would I find that? What if I wanted to go this way? So start here and go in the negative direction. Who could tell me how would I do that?
Negative 11 pi over 6.
Negative 11 pi over 6. Well, if I start here, what they say, start at pi over 6 and then subtract 2 pi, right? That doesn't kind of make, it doesn't kind of make that kind of stuff intuitive sense. I like to think of it as negative 2 pi plus pi. Yeah, you could just subtract 2 pi. Okay, so if we start at pi over 6 and we subtract 2 pi, I get, that's pi over 6 minus 12 pi over 6, which give you negative 11 pi over 6. You get that? Okay? I could subtract 4 pi and come up with another one. I could subtract 6 pi and come up with another. So if I want to find one that's coterminal, I could add 2 pi. If I want to find another one that's coterminal in negative direction, I subtract 2 pi. I don't think I have to do more of those. What if they said sketch? Sketch negative 5 pi over 4. Could you do that? Where's negative 5 pi over 4? Without really, so without converting it and figuring out how many degrees it is, okay? 5 pi over 4, is that going to be bigger than pi or less than pi?
Bigger than pi.
Bigger than pi. So pi is, so the way I like to think about it, okay, so this is pi. That would be 4 pi's over 4, right? And then how many pi's over 4 more do I need? 1 pi over 4, which is 45 degrees, if that helps you think about it. Okay, so I'm going to go to here. And so, whoops, I messed up. That's positive 5 pi over 4. If I wanted to go negative 5 pi over 4, then I go this way, and it would be over here, right? Negative 5 pi over 4, positive 5 pi over 4. Yeah? Good. All right. What else do we need to know? We talked about that. Converting degrees to radians. Converting. Multiply because pi radians is equal to 180 degrees, right? So all you have to do is multiply, this is a equivalent conversion fact, so there's pi, this is equal to 1, right? Pi radians in 180 degrees. So say, for example, what's 135 degrees in rads? Okay, and in rads means, where are you going? With your cell phone? What? You just get a text message and you gotta meet someone?
No.
Okay. Okay, 135 in rads. So I'm gonna go 135. I'm gonna multiply that by pi over 180. Okay? And look for things to cancel. What number goes into both 135 and 180? Bigger. Really big. You'll get familiar with some. 45 goes into 135 how many times?
3.
3. Divide this by 45, you get 3. Divide this by 45, you get
4.
4. So that's equal to 3 pi over 4. Now you could reduce it and just keep going, but you write that as 3 pi over 4. The other thing, you'll get used to seeing these common angles all the time. How about 22.5? Just see if you could do that to radians. 22.5 is half of what? It's half of 45. Would you guys stop with the messages?
Yeah, I can turn on my question.
Yeah, it would be good. How about if you just put it away? Okay? 22.5. So that's half of 45. How many radians is 45 degrees? Not pi over 2. Pi over 4. What's half of pi over 4? Pi over 8. So that's kind of the way I like to think about things. Think about some angles that you know in radians, and you can do it a lot quicker in your head. Or you could go 22.5 times pi over 180, and then you would divide that into that, and you would get that's equal to pi over 8, like that. Okay? Radians don't have units on it. Okay? So if they say, well, let's just do, what if they say 37 degrees? What would I multiply by? Pi over 180. And that's not one that's real, you know, it's not a nice even one. So then you'd actually take 37, multiply it times pi, and divide it by 180, and you get it rounded off, you know, let's say to the nearest tenth or something like that. Okay? So you want me to do that? Get your calculator. There we go. But there's also a way to do it. I kind of forget. Maybe I'll remember. So if you're on your calculator and you go, where'd my calculator go? Second quit 37. Second quit 37. Pi, you could just type in pi because that means multiply, which is above the arrow key. Divided by 180, you would get 0.645 radians. So that's equal to 0.645. You don't have to write radians, but just to make sure you know that's what it is. Your calculator, I think, can also do that for you. If you did 37 second pi, and I think if you go to this thing angle, second angle, and where is that? Radians, is it R? No, that's not gonna do it. No, I'll figure it out. There's a way. But it's easier to go from degrees to from radians to degrees. Okay, going the other way, converting, and then we'll be done, converting radians to degrees, okay? Anyone know how to do that? 180 over pi. You just do the opposite thing, okay? So convert, multiply, a different color. Multiply, I didn't get a different color. Multiply by 180 degrees over pi. And if you ever forget, right? So if you want to do radians, so say I want 3 pi radians, and I want to convert that, okay? Usually the radians have pi's in them. Not always, but you do something like this. What cancels out from top and bottom?
Five.
Pi's, and you get that's equal to 540 degrees. Now, what I tend to do, like what if they wanted to do negative 5 pi over 6? This is why I tell you those things in the very beginning. What did I say that pi over 6 is? How many degrees is that?
30.
30 degrees, right? A pi over 6, you should memorize that. Pi over 4, pi over 3, pi over 6, pi over 2. Pi over 6 is 30 degrees. What's 5 times 30?
150.
5 times 30, so that would be negative 150 degrees, like that. So if you think about it in terms of pi's, it's kind of quicker to do. You see, so if you know, so what if I did like 7 pi over 4? How much is a pi over 4?
45.
45. What's 4 times 45? 180. So that's kind of a harder one to do, but you'd have 7 times 45, right? Which is whatever that is. 180 plus 135. What would that be? 315? 315. Or you can do negative 5 pi over 6 times 180 over pi. You forget how to do it quick, and you cancel out your pi's. 6 goes into 180 how many times? 30 times, and negative 5 times 30 gives you negative 150 degrees. See, which is what I got over there. My way's a lot faster. All right. That's all I'm going to say. Your homework is, do you have any questions?
No.
Page 261. You're gonna whine, but it's quick because it's just convert this to this, convert this, draw this angle. You'll get it. 12 to 88. Well, I mean 12 through 88 every third. Okay. Every third, no, not every other odd, every third, because I want you to do some even ones too, where the answers aren't in the back of the book. And then 113 to 115. Okay? And that's all she wrote. And I talked to you for 33 minutes.